In this lesson, we're looking at hydrates and how we can represent the amount of water that's contained within a hydrate. So recall that a hydrate is a compound that has a specific number of water molecules, which are called the waters of hydration, bound to each formula unit. So it's an ionic compound, and for every formula unit of the ionic compound, it has a certain number of water molecules associated with it. So for an example, MgSO4 7H2O, so that's a hydrate, and it's telling you that there are 7 molecules of water bound to every 1 formula unit of magnesium sulfate. Another way to say that is that there are 7 moles of water for every 1 mole of magnesium sulfate. And some terminology that you'll hear is when the waters of hydration are removed from the ionic compound, we call that the anhydrous version of the ionic compound. So one of the ways we can represent how much water is in a hydrate is a mass percent. So the percent of water in a hydrate is going to be the total mass of water in the hydrate over the mass of the whole hydrate times 100%. So this is very similar to our previous percent composition calculations, and the masses that we're going to use for the calculation can either come from the molar mass, if we know the formula, and more often they come from experimental data because we're trying to figure out how much water is present. So let's first look at an example where we know the formula so we can calculate the percent by mass of water by using molar masses. So if we assume 1 mole of the compound, we figure out the molar mass of the hydrate. So there's 1 magnesium, 1 sulfur. There are 11 oxygens and 14 hydrogens. So be careful there. Remember that that 7 in front of the H2O also applies to the oxygen, and we need to combine that with the 4 oxygens in magnesium sulfate. So when we add that all up, we get a molar mass of 246.52 grams. Remembering that we are adding here, so our molar mass has 2 decimal places, just like all the molar masses we used in the calculation. Then we need to know just the mass of the water. And in this case, there are 7 of them. Okay, so what is the mass of 7 waters? So we've got 4 hydrogens and 7 oxygens. So the mass of 7 waters is 126.14 grams. So now we can calculate the percent of water by taking the mass of the water and dividing by the mass of the entire hydrate. So 126.14 grams divided by 246.52 grams times 100% gives us an answer of 51.168%. And if you look at those 2 masses that we've used in this calculation, they both have 5 significant figures, which means our answer should have 5 significant figures. So more often these calculations are done using experimental data. So a 50-gram sample of a magnesium sulfate hydrate contains 24.4 grams of anhydrous magnesium sulfate. So this can be done in the lab. If you take a 50-gram sample of the hydrate and you heat it, that's going to drive the water out of the hydrate, and leave you with the anhydrous form, which you can then weigh and find the mass of. So then you can figure out how much water was in the hydrate to begin with. So from the experimental data, we know that the mass of magnesium sulfate hydrate was 50 grams. We know that the anhydrous magnesium sulfate, so after all the water is removed, is 24.4 grams. So using those 2 numbers, we can figure out what the mass of water is by subtracting. So there was 25.6 grams of water in that sample. So the percent of water is going to be 25.6 grams over 50 grams times 100%. And this gives us an answer of 51.2%. And in this case, the masses we used were only accurate up to 3 significant figures, so our answer can only have 3 significant figures. So the other calculation that we can do is figure out actually what the formula is. So with the magnesium sulfate, that we were just talking about, there were 7 waters. So how can we figure out how many waters there are? Figure out that number that goes in front of water. So we're going to look at this example. A 50-gram sample of a hydrate of barium hydroxide contains 27.2 grams of anhydrous barium hydroxide. So what is that value of X? So we know that that X tells us about how many moles of water there are for every 1 ionic compound formula unit, right? So we need to work in moles. So we're going to determine the number of moles of barium hydroxide in the sample, and then the number of moles of water in the sample. So we're going to need the molar mass of barium hydroxide and the molar mass of water. So we'll figure those out to begin with. So now to figure out how many moles of barium hydroxide were in this sample, well, we know that there's 27.2 grams of anhydrous barium hydroxide. So we take that mass and we convert it to moles using the appropriate molar mass. And we find that we had 0.15874 moles of barium hydroxide. And you don't want to round any answers yet too much. Okay, then for the amount of water, well, we need to subtract 27.2 from 50 to find out how much water we have, and then use the molar mass to find the number of moles. So when we do that, we get 1.26526 moles of water. So there's our molar ratio. We know that for every 0.15874 moles of barium hydroxide, we need 1.26526 moles of water. But those are pretty ugly numbers, so we're going to do what we did when we were figuring out empirical formulas. We're going to divide by the smallest amount of moles. And in this case, if you've done it correctly, that will always be the ionic compound, because we want the 1 in front of the ionic compound. So if at this point, your moles of ionic compound are not less than those of water, then you've made a mistake. So check your work. So we're going to find that ratio by dividing the moles of water by the moles of ionic compound. And when we do that, we get 7.97. And just like with empirical formulas, you want to be fairly close to a whole number. And so this is close enough to 8. So this tells us that X in that hydrate was 8. So the formula is BaOH2 and then that dot 8H2O, and that would be called barium hydroxide octahydrate. Look at another example. Determine the formula for the hydrate of sodium carbonate that contains 37.0% sodium carbonate by mass. So same first step, we're going to convert that 37% into moles. First, we're going to have to get a mass, and if we just assume 100 grams, we know that in a 100-gram sample, there would be 37.0 grams of sodium carbonate. So we're going to need the molar mass of sodium carbonate, and again, we'll also need the molar mass of water. So we've got 37 grams of sodium carbonate. Convert that into moles. We get 0.34968 moles of sodium carbonate. Then we subtract to find the mass of water, and then find the number of moles that equals to, and we get 3.4961 moles of water. Okay, so then what are we going to do? We're going to divide by the smallest, which should be always the ionic compound. So 3.4961 divided by 0.34968. You may be able to see what that's going to end up being, but it's really close to 10. So in this case, the value of X is 10. There are 10 water molecules for every 1 sodium carbonate, and this would be called sodium carbonate decahydrate. So those are the methods that we can use to represent the amount of water that is present in a hydrate.